We've all the NIST people have worked with string pots. It's a pretty basic thing. LVDTs, we work with those all the time, measuring displacement. Accelerometers, there's many types of accelerometers. I'm running through this really quickly because I want to get to, I don't want to go into a lot of detail here. I want to get into this idea of operating range. But there are these physical ways of measuring physical attributes. And somehow you as the researcher and the NIST staff need to make a choice as to how to do the measurements. This is an earthquake sensor. I'll have an example of this in the back. There'll be some other examples of sensors here. Strain gauges, I think most people in here are familiar with them and have used them in labs. But there's a lot of issues with strain gauges as well. It's not something you just pick one off the shelf and paste it on. There's a lot of issues there. Load cells are generally strain gauge based, at least the ones we use. So again, you're getting back to this idea of a strain gauge as a basic measurement unit. Pressure is also often a strain gauge. Most of the pressure measurements we do are strain gauges. So now I want to get into the last couple minutes here and introduce this block here, that instrumentation is an art. And I would hope that if you take away anything from this, the younger people, either students or young faculty, realize that it is an art, and that if you just go out and buy something off the shelf, you're probably going to get it wrong, or you may get it wrong if you're doing something that is out of the ordinary, which we do in research. You have to consider three domains: amplitude, time, and frequency when you pick instrumentation. You can't use a vibrating wire strain gauge to measure dynamic strains, for example. There's a lot of issues like that. You can't use a piezoelectric accelerometer in general to measure earthquake motions, because it doesn't have the low frequency response. All kinds of things like that that you really need to consider. And this is one example. These are LVDTs here. This is a load frame. This was a foundation test where we were doing quasi-static testing on a foundation. And it worked fine. We've got a reference frame at the top. We've got these beams hanging down. That's fine for static measurements, but if you tried to shake that at all, and actually it became a problem for the low-level measurements, just the ambient vibration of this thing, it's not suitable for dynamic. And it's not just the sensors, it's the whole setup. I talked about piezoelectric accelerometers. If you just pick a nice Endevco accelerometer off the shelf and say, wow, this, it's a 10G accelerometer, this will work. You look down and it's only measures down to 1 hertz or half a hertz, and that may not be adequate for earthquake testing. So there's a tool that, it's not a new concept, but I've been working with colleagues in seismology to try to better define this and standardize it, called operating range. It's a tool for considering both amplitude and frequency ranges. It doesn't get into time. But it's a way to compare instrument operating range, the range of combined sensor and data acquisition with your measurement need. You have to consider time separately, but you have to do that anyway: sample rates, storage, that sort of thing. So this is the basic idea of an operating range. Its frequency is the x-axis, and amplitude. Amplitude is kind of weird because this is a Fourier spectrum, but Fourier spectra don't work here. So generally it's, you go back to the acoustics arena and you use narrowband RMS or peak values. The 3rd octave, 5th octave, something like that is pretty standard. So it's narrowband, so you can actually compare amplitudes. And then you define the range of the operating range of your instrumentation, both in terms of frequency bounds, upper and lower, and amplitude bounds, maximum or some clip level, and then a resolution level, which is often the noise, maybe not the sensor, maybe it's the noise of the data acquisition system. Maybe it's the ambient ground motion that you've got. But it's some noise level that you can't resolve below. In the middle of all that is a box or a shape. It's actually not always going to be a box. But it'll be some shape that's your operating range. That's the range you can get decent data. So if your phenomenon that you're measuring is within that operating range, you're fine. Okay, so you've also got to define your phenomenon. I want to measure strain on steel, and if I use a resistance strain gauge, it's going to go down to about, resistance strain gauge systems don't go much below about a microstrain, and resistance strain gauges, typical ones, only go up to about 2,000, 1 to 2,000 microstrain. So that defines your range here. Frequency range depends on your signal conditioning completely for that. If you have a vibrating wire strain gauge, your whole range is basically low frequency or DC. But you can define that range, and then you have to look at what you want to measure. Am I measuring static strains, quasi-static, dynamic? If I'm measuring vibrations, ambient vibrations of a bridge, or ambient strains from vibrations of a bridge, it's going to be very different than if I'm pushing with a static cylinder. So the basic idea is that you define your phenomenon, and if it's outside the operating range, you've got to figure something else out. Now there's a paper that was just published in last month in Seismological Research Letters. I've been working with a bunch of colleagues at the USGS and others, developing and defining this idea of operating range for earthquake sensors. And everything in here is transferable directly to strain, displacement, and others. So it's Seismological Research Letters just last month, July, August, or 2 months ago, July, August 2010. And John Evans is the primary author. But what it does here is it defines, and there are, those of you who know time series analysis, digital signal processing, you kind of know that it's hard to combine on the same plot a clip level, which is an absolute level, and a noise level, which is a power spectrum. And so we've developed a framework that you can combine the two of those in a rational way. And so you've got, at the top, you've got a clip level of the sensor. This is RMS amplitude, half octave bands, meters per second squared. You've measured a noise level of the sensor. This is the noise level of this particular accelerometer, and I think it's actually the same one I have back there. I think it's the Kinemetrics epicensor, I'm not sure, but it's a strong motion, a good strong motion accelerometer. And then you compare that, and the frequency range goes from about 100 hertz down to 0.01 hertz or so. The noise level is not constant, but this area in between the noise level and the clip level is your operating range, and between frequency bounds. So this area, I couldn't find a good way to shade it in. That's our operating range. The green lines up there are sort of peak values of different earthquakes that we might want to measure, and they lie within that operating range. Okay. So that's the basic concept and I think that's my last slide. I couldn't find a way to, or I couldn't figure out a way to extend that to what we do. I hope to do that later. But I think the operating range is a very useful concept. And what I'm trying to get at here is you need to understand the limitations and constraints of your instrumentation system, which is the sensor signal conditioning digitizer, in terms of time, frequency, and amplitude. Compare it with your needs and make sure that you're in the sweet spot of the operating range. So with that, thank you.